is what I didn't have time to do last time, and then we pass to Navier-Stokes with Simon will give it. Just little announcement. So we are not fitting to 8 lectures, so we are giving 9 lectures. But the 9 lectures will be also on Friday, because the next week Simon is traveling for the carnival. So that's. But on Friday, in compensation, we promise fruits and food in a break. So don't worry, nobody will die from hunger. No? So on Friday we expect to have 2, like instead of 2 hours, we will be like 3 hours in total, or a little more. Okay, so I'll summarize very shortly what we did, and then just because I want to give a conclusions in a bit more detailed form. So summary of what we did. So what we did, we considered the shell model, which is essentially models geometric progression of scales by evolving dynamical system for the variables, which is kind of velocity, which is called shell velocity for each scale, which is complex number. And then we had a model for this, which has forcing, dissipation, and so on. And we talked that there is an inertial interval which corresponds to very small limit of zero viscosity, where there is no forcing, the scales where there is no forcing, no dissipation. And it means that in this region we have scale invariance. Invariance of equations. So equations are scale invariant in these region of scales, and from that scale invariance, it was with parameterized by the Holder exponent h. So there is a family of symmetries. And then we found that there is another symmetry, which we call hidden symmetry. Hidden scaling symmetry. And what we did, we obtained some kind of diagram. So if you have any solution of the ideal model in the inertial interval, what you can do, on one side you have a scale invariance of the equation, so you can apply the scale invariant and obtain another solution. Will be u prime t prime, and that's essentially the transformation is TUN to lambda 1 minus ht lambda h un plus 1. So it depends on for any h which is Holder exponent, you can make this transformation and map solution to solution. And there was another side which was obtained by rescaling. And rescaling was depending on m. So essentially, we were fixing some reference shells, making rescaling, which gives us different field with different time. So this field, small u, it was solving the shell model equation. Shell model equations. And the new field, it will solve another system of equations which has what we call hidden symmetry. Transformation. And important here, there is no h. There is no h in this symmetry. And this system, this transformation, just in a similar way, it gives you a new solution to the same equation. So this is a rescaled system. So important is that this diagram can be closed just by doing rescaling, the same rescaling on the bottom level, and this is actually the whole essence of a hidden symmetry. Is that you see from left side to right side you just go by rescaling, but the left side in the left side you can apply any scaling symmetry with any h, and it will be the same as applying just hidden symmetry transformation without h. So h is lost. So that means that we have kind of fusion of h's. So fusion of symmetries for different h, they become just a single thing. So that's first part. And the second part, what we showed was structure functions. Structure functions. So what we did, we defined structure functions as sigma p. So this is not summation. It's just maybe not the best notation. So this is just a function depending on scale, and this is defined slightly different from what is usually done in the literature. So we define them for amplitudes. So these amplitudes as moments of amplitudes, and then what we derived using hidden symmetry. So we derived that this can be written by, well, this derived directly. So this is derived that it can be written as averages of certain measures, the x. So x is a sequence, inverse sequence of multipliers. No? So details are not so important. Important is that we can derive it as a mass of certain measure, positive measure, and these measures are related. So these measures are related by iterative relation. So iterative relation is that one measure is obtained from another. So this is a linear operator. I'll just give it again because last time I wrote it in some bit strange way. So if you apply this operator to the measure, you get another measure which is x0, p. Then there is a conditional probability measure coming from hidden symmetry. And then there is mu p of smaller m dx minus. So x minus is shifted for sequence. So essentially you take the, sorry. It's related in different ways. So LP, it maps any measure, positive measure, to what will be x0p, conditional probability. Like this. So you give me a measure, it gives you a new measure. And just transformation, and this transformation, last time I wrote some extra term, it was not necessary. But anyway, so you give me a measure, it gives you another measure, and it essentially, this is nothing else as the multiplicative Markov process. So this is actually multiplicative Why? It's because so if you you take certain measure, you multiply by kind of random number, which is with a certain probability distribution, but conditioned on the previous ones. And then you do it again. Multiply by a new random number with the same distribution, conditioned on the previous one. So this is multiplicative random process, which we know gives you power loss, and this is essentially exactly the same what is done. So what is done is what we know from these multiplicative Markov processes is that the asymptotics is controlled by Perron-Frobenius modes. That means that this mu pm converges to, this will be Perron-Frobenius eigenvector, and then there will be Perron-Frobenius eigenvalue. So m times, so it's in m power, and then there is a prefect. So with Perron-Frobenius mode, which means that it's lambda p is an eigenvalue, lambda nu p is an eigenvector, so which is a measure. So this is a, we know how, this gives us the asymptotic behavior, and then you put asymptotic behavior back into this formula, and you get a formula for structure function. Zeta p. So here you have to translate lambda pm to lm zeta p. So this zeta p is just minus log 2 lp. So you have to translate lambda p to the 2 minus 1. No, so that's a formula. So that's essentially the result. So we can derive. So we have. So now let's make conclusions. So first conclusion is what was said is that power laws themselves, the fact that structure functions scale is a power laws, and together with exponents zeta p, they come from combination of hidden symmetry and Perron-Frobenius theorem. Put together, you get power laws, and you get all of them, and we can check it. So we can make numerical verification. That I hope I will be able to show from a computer. Essentially, what is numerical verification? Numerically, we have to verify this formula. This formula is actually much more general than the next, because this is just average of the first. So what we have is that not just structure function scale is a power law, but the whole measure scale is for the power law, which means that we just, so this is eigenvector, so it's normalized to unity. So and this is a measure that we can compute. So what we do, we just normalize this to unity and see that it does not depend on m. So numerical verification, so you approximate eigenvector from the formula that you want to verify. So this coefficient is just mass of the measure, so it's, we derive it, we divide by this, and this should be independent on m. Independent on m for each p. And this we check numerically. This if I will not succeed to show, this perfectly agrees with numerics.
How is the measures related to the solution, big U?
Well, essentially, that's the whole story. So the measure actually is defined. That's the whole idea that even though these measures, they are actually, it's not it's not theta. Sorry, u. No? So no more thetas, no? I hope. This quantity is written in terms of the original field. So the technical part is that it turned out that we can write this averaging in terms of averaging of the rescaled field. And whenever and not only averaging of rescaled field, but essentially in the average in the terms of multipliers, which I don't define, and multipliers are also functional of capital U, of big U. So somehow this is a long story that I tried to show last time. That's essentially the central part. So you first derive these measures, and second derive the iterative relation for the measures.
Is there U, the measure U, for big U, is there interpretation? What does it does, the measure?
Yeah. You can write it explicitly, both in terms of small u and big U. So it's just formula.
Is there interpretation?
Well, essentially it's a product. It's a mean of the product, but it's mean of the product in a slightly different way, because it's mean of the product of so it can be written in both cases, but I mean let's not get into these details, because we spent some time in the last lecture, and it was also not enough to give details. So essentially, but that's you can see who is interested in the derivation. You can see the papers. Okay, so this is one part. Another part is dependence of zeta p on p is typically nonlinear. Typically means that whatever typical functions you put here, it gives you nonlinear dependence on zeta p on p. So that's nonlinearity is natural. So just take the p which does not depend on x minus, and then you get moments. It's generally nonlinear. So this is what we have. The second thing is usual structure functions. Which is called now SP, and these are now moments in time of U, right? So this is different from these ones where we took amplitudes. So what's the difference? Actually, the difference is simple. As I just said, that the power law is not just appearing for structure function, it appears for the full measure. So it's actually structure. There is very strong power law dependence of the whole distributions that we have, and in particular, these structure functions come just from averaging. But if instead of averaging you put any other observable, you also get you also get power law. So this is what happens. So what you can actually show with an exercise, you can show that this structure function, instead of just taking average, you put some prefactor, you put some observable. And exactly this is x0, 2 minus 1, p over 2, d p, p dx. Okay, so there's a whole difference in this, which means that you substitute the same formula for the measure and get the similar formula power law with exactly the same exponent but different coefficient. So the different coefficient is because coefficient is now, so it's integral of this factor with an eigenvector. So there is usual structure, and then there is a branch of a lot of different generalized structure functions you can imagine by putting different prefactors, and you get power laws for all of them automatically. And the last part is intermittency. So I would like to stop slightly more on this. So what we have? So we have that from the amplitude structure functions. We have that they all scale at zeta p. And also we found that this is true for all real powers, positive, negative. So this situation also assuming that z function zeta p is differentiable. So this is, of course, we cannot prove, but so if this function is differentiable, but all the numeric shows it is, you can use what's called Gardner-Ellis theorem. This is from a probability theory, which gives you what's called large deviation principle. I will not write exactly the statement, but I'll write just kind of heuristic interpretation. So what it tells you is that that for large m, so it means that in the inertial range, in the inertial interval, exactly we work. The probability of, so you find this amplitude of order LMH. So if there's given h, you find this amplitude of this size with probability is of order L M J of h, where J is called rate function, where the rate function is obtained by Legendre transform. So it's supremum over p over all real part zeta p minus ph. Because Legendre transform of this function, you give the rate function, and it gives you probabilities. So what does it mean? So it means that whenever you have certain curve for zeta p, you take a Legendre transform. Important, it goes for 0. Since it goes for 0, so Legendre transform is what? So you take any point. This is a concave function, so you take any point, then h is actually, so what's Legendre transform? H is inclination of the tangent, and j of h is intersection with the vertical axis. And you see it's always positive, right? And it becomes 0 just in this point. So it means that the rate function is always positive. It doesn't have to be defined for all h, because if you have certain linear asymptotics, which is our case, then it means that there is certain h min, which is this inclination, and then h max from another side. And this is a picture. Okay. So what does it mean? This is the last thing. So what this picture means is, if I can remove. So first, so when j is 0, so this h0, when g is 0, the probability just remains order 1. So it means that almost everywhere for large M, almost always you will have the amplitude near lm0, h0, lm h0. So usually if you put amplitude as function of time, and it's usually, so you remember that this is picture. So usually, most of the time, it will be h0. So most of the time, it's h0. So whenever you take, if you want to see peaks, peaks correspond to smaller h, no? Because lm becomes small, so smaller h, bigger the value. So smaller h means this part of the graph. So these are strong events, peaks. So it means that whenever you want to have a peak, and smaller the m, bigger the peak, because it will be smaller h, for lm is a very small number, so every peak is just correspond to h, the event where h is smaller than h0. But smaller the m, the probability, the j is now positive, so probability become very small. So you see that exactly this question of exponents is directly describes how often you see the large, how often you see peaks of different size directly. So the peaks, or the bigger peaks correspond to smaller h, but they come with a smaller probability. So that's its intermittency. So this is already a visual connection between both, and I think I'm done. So if probably the last. Yes. I think that's okay. Oh, thank you.
Connect this
You should use this.
solvable shell model.
Hmm?
Connect this with the solvable.
Well, this is everything is available. Everything actually for the solvable shell model, we didn't need amplitudes, essentially because we never had 0, but we had this structure we had. Only I never wrote it explicitly, but you can try to write it. And what is important was this relation. So this relation was without dependence. Remember, so that we had different. Actually, the Wn that we had. It was Wn. No? Yeah, Wn that we had in shell model were exactly the multipliers. And as we wrote, the probability distribution at the end, the probability distribution had this Markov structure. Not even a Markov structure. It was a structure of the product of independent variables.
Because there the peaks correspond to the fact that when things synchronize.
Well, yeah. But that's different. That's a different point of view. So There you can see the reason why the peaks synchronize directly from dynamics. This system is more chaotic, so there is no, this synchronization is not a clear fact. But from this theory of large deviation principle, you can connect the peaks just from the scaling laws. So it turned out the scaling laws is sufficiently already to control peaks. So certainly, a solvable model will give him much more transparent picture. So I just wanted to show this picture. So this picture shows the, on the main picture, it's exactly a collapse of these measures, just projected, just marginal part, which projected on first coordinate, and shows how it collapses for different p. So this is p minus 2, minus 1, 4, 2, 4, and 6. So you have a very good collapse, and insets is just to compare, if you compare with the collapse that you would like to do using the Kolmogorov theory, just to show that collapse is really considerably different from Kolmogorov scaling. So, but anyway, you can forget about inset. So you see the collapse is very good, and collapse is done for, you see, so for in each picture there is 8, 9, 10, 6 different reference shells. So six different curves here collapse to the same, which is essentially what we wanted to show. So that's confirmation of the Peron-Frobenius mode question. And then, for example, this picture is the rate function that you can compute numerically. So that's the form it has, which controls the multifractal behavior. Okay, so that's it. So now you yeah.
We're using the shell model as important if you consider just like an infinite dimensional differential equation. Would this work as well?
Well, this will work as well as long as it has the same symmetry group, and we will talk about this on Wednesday. So exactly, so why it will work for any system which has the same symmetry group. So far we just showed it directly for the shell model. Well, you need this? Not now. No.
Thank you. It's on. We can. All right. So okay. So the next part is basically to try to escape from zero dimensional space. So basically, both of the shell models that Alexei presented in the last 2 lectures, they provide a very clear dynamical path to intermittency. And basically, this path is mediated through the definition of multipliers, so which is this x here, which are the ratio of those guys, and basically they give a connection from dynamics to intermittency through essentially products of multipliers. And so the question that we may ask is, okay, how specific is this picture to the shell model? And is there a way that we can hope that this picture carries through say, the Navier-Stokes equations. So that's basically the topic of today, is basically to parallel the introduction of suitably defined multipliers in order basically to reach this step and this step, but for the Navier-Stokes. That will be basically the program. I don't know if we have time, but we'll try to make the best. So basically, that will be the topic of this course is just hidden Navier-Stokes. And so one of the big issues is to define what we mean by multipliers. What are those multipliers which seems to be the pivotal objects in this mediation from the dynamics to intermittency? And so we can start from history. So also some ideas that come from Kolmogorov, that basically one data-driven, essentially, definition of multipliers are the so-called Kolmogorov multipliers. So just to remind the framework, where we are dealing with a field. So at each position of space and times, we have velocities, u of x, u of x prime. And so we were previously interested to the increments u of x plus L along a certain vector ei minus u of x. So that's basically the definition of the increments. And so the idea of multipliers is not to consider the increments, but rather ratios. So we take the separation between 2 points, which are well, you have a distance L here, along a vector, and we divide it by the separation between another vector, say call it J minus Ux. Of course, we are dealing with vectorial quantities, so let's put some K here. And so this defines basically a quantity that we may call omega AJK. So here there is I've took the ratio between increments at the same distance. So in order to have something which may have some evolution, I'll put a lambda here. And that basically a multiplier which a priori will depend on lambda and L. Okay. So that this definition, basically, is what we mean by Kolmogorov multiplier.
Average?
Kolmogorov. So I take a given space, I take increments over one direction from L, increments with respect to another direction, and I just do the ratio of those types. And there are ratios, and so they were introduced in 62 essentially. And so the idea is that so as usual, if we define say P star of d omega is nothing but the the turbulent measure associated to E, G, K in d omega. Okay, so I can. So let me just remind that what I mean by this star is, as usual, the turbulent measure. So this is the limit of nu goes to 0, of limit of t goes to infinity, 1 over t. Dt. Okay. So the idea is that suppose that we can define this object, so that this object exists, then basically the conjecture, and that's what we call the K62, Kolmogorov 62 hypothesis of refined self-similarity. So that basically this quantity does not depend on L. So basically there is a well-defined limit when L goes to 0 of this P star. So this here depends on L, sorry, of L of d omega. Call it P star 0 of d omega. So here, basically, a priori, this guy depends on L and on lambda. P star is just basically, I take the limit of these guys. Suppose that those guys satisfy the Navier-Stokes equations. So they will have a nu here. They will also have a t. So this will be nu t. I take the limit of this guy when I go to a stationary state. I take the limit when nu goes to 0. This defines me a measure. And so from that, I can define the push forward of this measure, if you want, the law of the Wijks.
These stars should also depend on lambda. Depends on L and lambda, but not on T. Right?
Yeah, exactly. If you want, so let's put it. Let's put it this way: P star of L of lambda. Maybe it's a better way. Okay. So basically, when you let L goes to 0, this guy, which depends on L and lambda, will be a function of lambda only. So what it means in practice, so that's in the jargon that's called intrinsic refined self-similarity. Okay. So in practice, what it means is that basically the measure which depends on nu, P of nu L lambda d omega is independent from L for basically L between, say, a large scale and eta. So that's where, let us just recall that this range of scale here is basically the range of scale where we expect some scalings for the structure function. So here we are at eta. So here we expect something proportional to L zeta p. And here there will be just some regularization. So that's what we define as the inertial range. That's what we expect. So basically, if we want to test this conjecture, we just have to test whether we can just have an idea of whether this is true, at least for a finite viscosity in this inertial range of scales. Okay. So what do we see in experiments? So observations. So in order to simplify, we'll just consider, say, omega x, 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 okay, which is the u x of x plus L ex minus u x of x divided by u x of x plus lambda L ex minus u x of x. So what do we see? So this basically is something which approximately is prescribed by a Cauchy distribution. Cauchy with parameter which we call it omega, lambda, and gamma square. So what is a Cauchy distribution? It's a distribution which, so we can write P Cauchy of d omega. It's 1 over pi times gamma times omega minus omega lambda square plus gamma 2.
Why are you calling omega x? Why is there 3 x's?
Because I have, so those two. So this one here is this one. This one here is this one. And this one here is this one.
That's I jota k.
I jota k.
Plus geschreven x.
Ah, yeah, because AJK, so, okay. You want, so AJK are in either 1, 2, 3, or in X, Y, Z. So X is the first direction, Y the second, and Z the third.
And then for lambda, there also should be like an inertial range for lambda, right?
Ah, okay. So if you want so it's interval for L for eta L1 and lambda L eta. So the both of the so basically both of the quantity which intervenes in this ratio needs to be basically in the inertial range. That's,
When you let L go to 0, I'm saying like the quantity depends on lambda. But
yeah.
there should be an inertial range for that also.
No. So basically, what I'm saying is that a priori, so this limit, this is the claim. So fixed lambda, take lambda equal 2, or like lambda equal 1/2. Take the limit L goes to 0, then you get an object which exists and for which lambda equal 1/2 fixed. You see, for all lambdas, the limit of P of L lambda converges towards something. That's the idea.
But it can be different. For lambdas different will be different.
Yes, yeah, it depends on lambda. It depends on lambda. So that's, yes, exactly. Good point. So, okay, so so usually it's, so this gamma here, it's basically a shape factor. And this is basically the average. So if you want to see a collapse, usually what you do is you say divide by gamma. Up 1, and you will have omega tilde. Omega tilde is omega over gamma, and omega over gamma. So what you observe in omega tilde, yes. So this is the observation. So let's first do a plot. Yes, let's first do a plot. So we have, say, omega x, x, x. And let's first do a plot in using log coordinates, okay? So usually, basically, you see that this has some fat tails here. There's an omega square which appears. So typically, when you plot the log of the PDF of this guy against the value you can take, this is what it looks like. Okay. Here you have a slope -2. Okay. Slope. Yeah, there is a minus by 2. And this is the log, so let's put right. Always negative. The log of the PDF is something which will be always negative. This is what it looks like, and that's so I take a lambda equal say 1/2. This one was with L over 2. So this is what I observe.
What are the x's?
X is just I'm taking an increment along the parallel direction.
So it's W on a horizontal, right?
Yes, exactly. So that's omega x, x, x. And horizontal, it's, if you want, P of the omega.
Directed upwards.
Directed upward, if you want. Yes. So that's when you take a first L. So, okay, and then I take another L prime. Something very perfect. The collapse is perfect. So it's what? Yeah, exactly. And basically, it's basically rather P of L lambda for L in the initial range. So that's basically typically what we see. Like if we want to test, so that's the picture we have. That's just I'll put P star to simplify. But that's basically observation from numerics. Lambda, yes. Yes. Yeah, you're right. Okay. And so the devil is in the details. So basically, usually, so this has been usually taken as evidence that okay, looks good. So there is a small deviation if you look at basically what's happening here. Typically, so when you look at in more details, typically. So what you see is that, so now I put the PDF but in usual scales. So it's omega x, x, x of L lambda L. And that's P star, okay, of d omega of lambda. And that's typically what you see for the first L up. You have that's the one in red. And then basically what you see is usually that you take another L perhaps it collapses, perhaps it doesn't collapse. It's not so clear. So if there is evidence for basically that the fact that they kind of superpose, but not quite. And then basically the value here, so that's omega lambda. So that's typically 0.2 for lambda equal 1/4, 0.4 for lambda equal 1/16. It depends on lambda. Okay. That's an observation.
Center.
The center, yeah.
But the rest
So
is
it's,
the same.
yeah, so it's here. It's so I've cheated a bit. So that's the tilde one. So what it's plotted is omega lambda over gamma. So I center by basically the shape factor, which is more or less the variance of your distribution, and then you have a single number which characterizes, which is the average of the riskier distribution, and this is typically what you see. So there is approximate collapse, which depends on lambda, but here there is some kind of discrepancy here, and so there is at this point we can say plus. So there is a apparent universality of P of d omega with respect to L. Okay, so you see, okay, so maybe it's interesting to consider at the ratio. On the other hand, for those specific ratios, there is an instructive calculation that can be made, and this calculation is the following. That just if you take again this Gaussian or favorite Gaussian heat, okay, well you impose that the correlation is U0R is U0 square 1 minus R psi for psi in say 0,2. Then you find that the ratio of lambda R over delta U of R is indeed something exactly as a Cauchy, which has for which we can compute the average and the shape factor. And here basically we have explicit expression. So for example, delta is 1/2 of lambda psi plus 1 minus lambda minus 1 psi, and gamma 2 is lambda psi minus delta square. Check, that's true. And so basically the observation is that delta over gamma 2, so delta over gamma 2 is a function which in general depends on lambda and psi, always. So basically, if you plot now the same thing, 1 over gamma of this guy, this will approximately behave as delta over gamma 1. Okay, and this basically is a function which depends on everything. So basically, this quantity, compute the ratio, at least in the Kolmogorov sense, allows you to have an apparent universality because the tails here are converging, but all the information about the statistics, which is this guy here, is basically concentrated in this number, an average which is usually very poorly defined because of the fat tail, so it's very hard to have very good estimates of this average. So basically, the apparent collapse of the statistical of the degeneracy of the Kolmogorov multiplier, it may be due simply to some type of statistical degeneracy of those quantities. And so for this reason, basically, the Kolmogorov multipliers, which are the historical multipliers, are perhaps not the good quantities to take a look at. And in the same way that, Alexei introduced some generalized multipliers, the hidden symmetry for Navier-Stokes will be a theory for generalized ratios of including those ones, but more general than that. And we do a short, a 5-minute break before we tackle this question.
It shouldn't depend on each of them, K, right? It shouldn't depend, right, on the shape on each of short in K.
The moral of this first part is that we forget about the Kolmogorov multipliers. We don't know that there's a whole debate on the turbulence community whether those are interesting quantities or not. So let's forget about them. Let's forget about them. So let's basically now try to make some ratio appear that will be interesting for our business. And so that's what the second part is. Basically, we are going to follow the steps of the Sabra to propose a dynamical rescaling of the Navier-Stokes. Okay, so remember for Sabra, we had a reference shell, M, okay, from which we were defining several things. First, an amplitude, so reference shell. An amplitude. And then, basically, we could define some new some rescale variables, u, n, say m, which were just the old variables divided by a of m. Nu. Okay, and the thing that the gist is that we are doing that together with the time rescaling, which was introduced as d tau of m. Nothing but dt over Tm, where Tm was essentially a local turnover time, so Lm divided by Am. So those were basically the ingredients that we needed for Sabra. And then we did something. So we are going to do the same for Navier-Stokes. So for Navier-Stokes, we will use the same ingredients plus an extra one. Okay. So the ingredients are the following. So I will not take so I will start. Yes. So instead of m, I will set a scale L, which will be the observational scale. Okay. then basically I need to define, well, that's the first thing I need to define. So it's clear that the analogs of the use here that needs to be used for such model will be, in our case, some type of increments. So let us define increments that will be delta u of L, position x, and t. What that will be u of x plus L x t minus u of x. Let's divide them. U of x plus L x t plus u of x t. Okay? There will be a lot of delta, so I will color them like that in order to avoid mistaking them for some application. Okay.
Big X and a small. There's a big X and a small X.
Okay. So the same as so basically here it's a position, and here basically it's a displacement. Okay, so x is in R cube, and position is in R cube as well. So what it describes is simply, I have u of x here. I have up a displacement L capital X, and here I have a new field u of x plus L x. Small x, capital X. So capital X, a displacement, small x, a position. That will be the another vector. Yes. So I'll put this here. Then. Okay. That will be the. Already. Are important. So now I need to define, let's try to define an amplitude. So amplitude, we will define it through basically a functional. So basically, take, for example, so amplitude. I will define a functional A, okay, which acts on velocity field. So that's something which goes from, say, R cube to R cube. Okay? And for example, take something very simple. We can think of a functional as, for example, v square average over a sphere of radius 1 to the power 1/2. Some type of L2 norm. So in fact, we can take more. So basically, this represents. So if I am at a position x here, v or 0 here, up, I will just A of v will just average over this ball of radius 1. Okay. So in fact, we can. So in fact, what we need, we will need. Is not specifically this form. It can be anything, something like more generally. It needs to have the property that if I multiply the argument by a scalar, then the norm of the scalar pops out times EV. So that's basically in A is a positive operator with homogeneity here 1, and basically it can be anything. So in particular, we may observe this property that will be useful at some point. That if we have this, the differential of A evaluated at V and dV. Okay, so it will be, so here it will be simply will be simply dA of alpha V dV for all alpha positives. This is an example. I want to have something which I take a vector field and I just prescribed an amplitude, so a functional which out of this vector field gives me something which is positive, a number positive, which has some this type of homogeneity property, and that's it. And that's no. Well, we'll see. It doesn't really matter. It will matter. It matters at what point. And just before, this is so in the shell model, the analog of this guy is so let's write it here. So in the shell, the analog of this guy was something that A implies on say U was U0 square plus alpha U minus 1 square plus alpha 2 U minus 2 square plus linear function in U. I take U, I output something which will be, okay, it has some form, but we don't really care, in fact. But it has basically this property. It has this property. So for example here, for this case, here, for example, here it will be simply V dV, okay, divided by A of V X equal 1. Just something like that. Yes, Nicolas? Yes. Yes. So basically, I can think of this as the differential apply to this linear functional, which is in infinite dimensional space. But okay, but that the analog here will be simply the gradient of this guy applied to du0. Yes. Yes. So otherwise, you see, this is the guy that we are going to take ratios of in the end. So that's why basically we need positivity. That was one of the basically requirements in order to apply the Perron-Frobenius theorem at some point. So positive. Positive. Okay. So we have the amplitude. So this is check. Okay. And that's from there, I think we are almost good. So now we can introduce the extra ingredient. It will be required to define this object. Okay. And the extra ingredient that we are going to use, okay, the extra ingredient is basically a Lagrangian trajectory. What it means, I will take x, so I will write it x star of t, x0, okay, such that basically d over dt of x star is equal to u of x star t. And this is basically the Lagrangian velocity field. So this is something that I may as well call u star of t and x0. Okay. So what it means? So this is has the property that x star at 0 is x0. Okay, and so if I do a picture, this will be, I will write it here. So I have basically up time t here. 0, I am at x0. Up, so that's the trajectory. And at time t, I am here. That's x star of t. Trajectory, up, that evolves in space, time t. X star of t, which depends on the initial position here. Okay. So U star basically is the velocity field. So basically U star, if you want, it's here. Okay, so this is U star is the velocity field at position x star of c of t at time t. Okay. I assume that my velocity field is sufficiently smooth at all time, so that the Lagrangian trajectories are well defined. I can just pick one. I consider an initial position. I evolve it with this equation. This gives me a trajectory which is defined from 0 to infinity. It does whatever it has to do. For Navier-Stokes, it's probably true. If we assume that we are dealing with physically reasonable solution, as we were dealing previously, then basically the velocity field is smooth. So basically, this equation has a solution. It's okay. But we have it's uniquely defined. There is absolutely no ambiguity here. That will be a matter for discussion later. Okay. So now that we have this extra ingredient, and let's put it here, so that's really this is new. Now I can define really the analogues of those two quantities. I will define first u, which will be basically a function which will depend on x and a rescale time. That will be nothing but the increments here evaluated along these Lagrangian trajectories at position x with the displacement x and at time t. And I will divide it by a quantity because I want to consider ratio. And the good way so I will divide it by something which I will call AL of t and also x0, where AL of t and x0 is nothing but the functional a here apply to this increment. I'll put it like that. So what is AL? So I am a scaling center. I take a sphere, okay, say, of reduced, so this has reduced here, diameter 12, and AL is just the average of the increments, or the increment squared, around this release center. That's AL. So that's basically AL. It's basically something which is a local amplitude. Dimensionally, it is a velocity. So if you want, it's a meter per second. I have AL, so I can define basically the same ID. I can associate. So this is something which is a velocity. I can also define a characteristic time, t of x0. It will be L over AL. Okay, and the final piece is the clock. That will be d tau. So d tau, it will be dt over tau L. So I have a new time here, tau, which appears here. I have an amplitude, which appears here. And of course, this object, it depends on the two ingredients that I basically introduced, which means it depends on L and x0. So what does it mean? Sorry? There's time t here.
So instead of t, you write tau.
I write tau, yes, exactly. That will be important. So basically, I rescale time according to the time that evolves along the Lagrangian path. So just as a small cartoon. So imagine that as a function of time, something that we drew multiple times. So that's AL. So AL will be something that will fill some burst. It will be 0. It's always positive. And that will be the typical, typical velocity, put it to 1, for example. And so that basically, the AL is basically represents the local peaks which are filled by this moving ball around this Lagrangian scaling center. And then basically there is tau. So tau, the new time, is something which if we can express as a function of AL, so it's nothing but AL over L times dt. So what does it mean? So when AL is big, so when you have a peak, tau flows fast. When AL is small, tau flows almost it does not flow. So what does it look like? So that's tau L as a function of time. So here, basically, there will be an event here. So here, it's almost typical, so it evolves linearly. Then you have a big event. Poof, it increases. Then you have it's typical, and say it will be. Is tau, sorry, yes. Tau, yes. Then you have something which is almost close to 0, so basically it will be almost 0, poof. Then poof, again a peak. Then it's beyond the typical 0, etc. So basically it's a quantity which is sensitive to the peaks of your coarse grained velocity field here. And so if we were to plot, for example, AL as a function of tau, basically, those guys here would be squeezed here, poof. And when you're almost flat, then it's almost as if the time doesn't flow, so it's contracting the time. So this is basically a contracting zone. So it's contracting. And this is expanding. Okay, so what does it look like? So if we want to have now, say, A as a function of tau, so it will be something that will be very boring. Let's plot it at the same. So A as a function of tau is something that so we have tau and AL. And it's something that here it's the same, and here poof, you have a big peak. So it will reach as high, but whoop, it will be something like that, and then it will be again very boring. And then so here you have something which is almost flat. So this part here, yes. So here, yeah, this will be. Let's put it this way. Yeah, so here, so let's put this basically like that. So something close to the typical. So it flows normally. And then when it's below typical, it contracts. So here it advances the same. Here it's below typical, it contracts. Well, but here, so I put 1 here. So that's the reference, you see. So 1, it flows naturally. Yeah, so it increases like that, so nothing is happening. Here, poof, I expand, and here I have a zone where I'm below normal, and then poof, so here, this zone here is totally contracted. And I go back to this zone here. So this zone is, goes there. And this zone, again, is here. Contracted to a point, and then, like that. You will see. It's this is where the magic happens. But let's pretend we do this. Because I want to do something boring in a sense. And to do something boring, I need to tame the extreme events. So I tame them in time. So because the short bursts happen in very short time. So basically, when they are too high, I just expand them. And then basically, the second ingredient will be essentially to rescale also this guy or this guy. So I will rescale basically the velocity field by essentially the peak. And so for example now, that's AL. But if I plot any type of norm for U, where I divide by the amplitude of the peak. So when I divide by the amplitude of the peak, it will come to 1, and then when it's too low, it will also come to 1. So it will be something very boring, basically. Very boring, so very, in a sense, very something that maybe we will have a chance to describe, and that will be more. So basically, by rescaling both the space and the time, I project something which is very bursty to something which is very very mild. So that's the idea in a sense. You rescale both in space and time. So it's that space and time. You stretch, you contract. So.
This is a longer Lagrangian particle.
And that's a longer Lagrangian particle. So this you may call, so this guy here, you may call it local time, for example, or local clock, or quantum clock, whatever you want. But that's exactly, basically, the time which is felt by the particle moving along this path when the particle averages the velocity field with the observational scale L. So the reference shell M in Alexei's lecture is basically an observational scale, a coarse graining scale, if you want, in the Navier-Stokes situation. What is boring? What is boring is is basically U as a function of tau. It's boring because it's it's perhaps too. That's what I want. I want to do something boring. You see, there's something which is very interesting, and I just boring. And that's and then then we can treat we can solve the boring thing and describe the exciting thing. That's the idea of this rescaling. And then because that's why that's the excitement. You produce something exciting from something boring. So that's basically a lesson for everyone. Yes, exactly. Yes, exactly. So d tau or tau basically. Let's put it here. Again, this is something which depends on L and x0. Let's leave for those questions for discussion later. For now, there is no conservation law in our system. But that's, I think, that's an interesting discussion to have at some point. Okay, so that's the ingredients that we needed. So we need this picture here. So now why do we do that? Basically, we do that because it turns out that if we do that, we can write the dynamics for this guy. Okay, and these dynamics we write now. So U tau solves basically the following equation. So assume that let's put it this way. So if suppose that U solves NS, okay. In the regular time t, then basically U tau we solve a new equation that we are going to call the hidden Navier-Stokes, which is the following equation: d tau of U plus lambda U times U dot grad U grad U plus grad P equal 3 lambda U times lambda U times nu L U plus capital F. Let's put it this way. Well, I need to define my objects. Well, basically, all the capital letters will be defined in that spirit. Okay? So P is basically a velocity field which we may call delta P L x star x t over L square, and F is something that we are up to some rescaling L over L square is nothing but the original forcing minus F, sorry, let's write it this way, delta L of F of x star x t, so the same definitions as those guys, and basically the prefactor are just dimensional prefactor. New L is nothing but our good old velocity, which is rescaled by what it has to L. And so now the interesting guy is this one here. Okay, and this one here, so that's an operator. So lambda u applied to a field V. Okay, will be, so that's again say R cube, R cube. Nothing but V minus something that is U of dA of U. So it's really something which is like a projection operator. So example, for A of V is basically our L2 norm average on the unit sphere, then lambda U of V will be V minus U times U dot V average on the unit sphere. Example. So, okay. So before I make this the other example, I'll just make this comment. So this basically equation, together with this definition, is what I call the hidden Navier-Stokes. And what you can see is that, okay, when those gradients here, all the operators which appear, they are with respect to the new variable, x. Okay? And the observations, I want to make two observations. The observation is that this is exactly like in Sabra. Exactly like in Sabra. In Sabra, let's just rewrite the equation for Sabra. So in Sabra, Sabra, we had U, the original dynamic was something like that. Okay, and the rescale dynamics, it was d over d tau of U n. It was Bn of U minus Un times the sum for I equal greater than 0 of alpha I times U minus I, B minus I, plus complex conjugate. This you may as well call lambda n of lambda n of B. So basically, take your observable A, defined this way, rescale your variables, do the computation, and basically you obtain exactly the same structure for the Navier-Stokes and for the Thalabard. Just the new dynamics is a projection of a type of projection of the old dynamics. Yes. Yeah, so here everything depends on x0. Well, everything, we'll see. But a priori, U is something which depends on x, capital tau, and L and x0. A priori, there is a, this is by definition. But of course, this will be the point. The second remark I wanted to do was basically just to show you how can show you how this operator appears, because I think it's interesting and that's really basics manipulation. So let's just try to write this equation, like try to derive it. So. So demonstration. So ID derivation. So we have remember that U is delta L of U of x star x t divided by AL. Okay, and that d tau is dt divided by 12. There's only two things that we need. And then basically, so that's the ingredients. Then eta of u. So we need to derive. So deriving by to t, we pick up a factor tl. So d over dt of delta L u over L, and that's L over AL, TL, times essentially delta L u dot divided by AL square AL minus delta L u A dot L divided by AL square. So far, so good. So here we recognize U here. Okay, and then the difficult part is this guy. But A dot L, it's A of delta d over dt of A of delta L of U. It's simply dA applied to delta L U dot. Okay? Because of the homogeneity property that, and the fact that A is homogeneous of degree 1, this is the same as U. Okay? And so here, in front of your eyes, you have it appearing. So let's write it. So essentially, dt d tau of U will be L over AL squared delta L U dot minus L over AL squared of U times dA of U delta LU dot. And so because well, that's just a linear operator in the second variable. So basically you can enter this guy is here. So that's nothing but exactly lambda U of delta L U dot times L over L squared. So basically, the lambda U appears just because we have rescaled our initial velocity field by something which is also time dependent. So this lambda U comes from the AL rescaling. That's the message. And then basically, it becomes pretty easy. Then we can just evaluate that dt of L of U will be dt plus U star of delta L of U plus U star grad of U. Okay, so here we are recovering almost Navier-Stokes except for a missing piece here. And so upon manipulating the Navier-Stokes, you can prove that basically you obtain exactly the right-hand side taken between points x star and x star plus Lx minus the missing piece. And the missing piece is exactly delta L U dot rad of U. And basically the hidden Navier-Stokes follows. So I will stop here. And basically on Wednesday we explore the consequence of this dynamical rescaling, and basically all these stories about fusing of symmetries and etc. etc. So I will stop here. In due time only. In due time.
And then if you take L goes to 0, more the big peaks become rare events.
Yeah.
So why do you want to make them bigger in your graph?
I make them wider.
Yeah, why?
Because
They become rare. Why do you want to make them bigger?
yeah, but they become rare. But basically, they are responsible for the signature for the non-Gaussian signature, or for the breaking of scaling invariance, if you want. That's really the phenomenologically. It's because you have peaks that when you start from something which is Gaussian on large scale, it's not at all Gaussian on small scales. So that's so you want to erase them for that reason. So there is some kind of magic appearing here, and so we will explore the consequence of this magic. But it's exactly the same kind of magic that basically Alexei talked about in the previous course.